Good day, esteemed researchers and curious minds tuning in from around the globe. Today, we delve into the fascinating world of large language models with our focus on LoRA, Low-Rank Adaptation of Large Language Models. This groundbreaking research tackles the challenge of fine-tuning these models for specific tasks, offering a more efficient, practical solution. Prepare to be intrigued as we explore how LoRA, with its compute and memory efficiency, revolutionizes the adaptation of models like GPT-3. Let's embark on this intellectual journey together. The motivation behind this research is to address the challenge of adapting pre-trained models, such as GPT, for downstream tasks. Traditional methods involve full fine-tuning for each task, which is resource-intensive, and becomes impractical for large models like GPT-3. The problem with full fine-tuning is that it requires learning a different set of parameters for each task. This leads to storage and deployment issues, especially for large models, due to the sheer size of the parameters involved. To overcome these challenges, the authors propose a parameter-efficient approach. The task-specific parameter increment is encoded by a smaller-sized set of parameters, reducing the computational and storage demands. Furthermore, a low-rank representation is introduced to encode the parameter increment, making it both compute and memory efficient. This innovative approach paves the way for more efficient use of pre-trained models in a variety of applications. In our research, we tackle the challenge of adapting pre-trained models, such as GPT, for downstream tasks. These tasks include summarization, machine reading comprehension, and natural language to SQL. As you can see in the figure, we compare the validation accuracy and number of trainable parameters of GPT-3 for various adaptation methods on WikiSQL and MNLI matched. The results clearly demonstrate the superior scalability and task performance of our proposed method, LoRA. We'll delve into the specifics of these data points later in the presentation. But for now, let's focus on the problem at hand. How can we efficiently adapt these large pre-trained models for specific tasks? Our research is driven by the need for a more efficient approach to fine-tuning models for each downstream task. This is particularly crucial when dealing with large models like GPT-3, where storing and deploying multiple fine-tuned models can pose significant challenges. The conventional approach to this problem involves initializing the model to pre-trained weights and updating them. However, this method falls short when applied to large models due to the high dimensionality of the parameters. Therefore, we are motivated to explore a more parameter-efficient approach that can effectively address these challenges. Our research proposes a more parameter-efficient approach to tackle the challenge of fine-tuning large pre-trained models like GPT-3. Instead of learning a different set of parameters for each downstream task, which can be computationally expensive and memory-intensive, we encode the task-specific parameter increment using a much smaller set of parameters. This approach not only reduces the computational burden, but also significantly decreases the memory footprint. This is particularly beneficial when dealing with large models, making the process of storing and deploying fine-tuned models more feasible. In essence, we're making the process of adapting pre-trained models to specific tasks more efficient and manageable. Our research introduces a novel, parameter-efficient approach to fine-tuning large language models. Instead of learning a different set of parameters for each downstream task, we propose encoding the task-specific parameter increment using a much smaller set of parameters. This not only reduces the computational burden, but also makes the process more memory efficient. Let's delve a bit deeper into how this method works. The task of finding the parameter increment is transformed into an optimization problem over this smaller set of parameters. To achieve this, we employ a low-rank representation to encode the parameter increment. This approach is particularly beneficial when dealing with large pre-trained models like GPT-3, as it significantly reduces the number of trainable parameters, making the process both compute and memory efficient. In essence, our method offers a more sustainable and efficient way to adapt large language models to specific tasks, without compromising on performance. In our research, we've taken a different approach compared to conventional methods. Typically, models are initialized with pre-trained weights and updated for each specific task. This means learning a new set of parameters for each task, equal in size to the pre-trained model. However, our method simplifies this process. We encode the task-specific parameter increment using a smaller set of parameters, making it more efficient. Now, let's talk about the results and insights we've gained from our proposed method, LoRA. We found that LoRA is a strong contender to full fine-tuning. It's effective not only in natural language understanding tasks, but also in natural language generation tasks. Plus, it's versatile and can be applied to any dense layers in deep learning models. This opens up a world of possibilities for future research and applications. Our research method was put to the test on natural language generation models, specifically GPT-2, medium, and large. We aimed to see how our approach would fare in these real-world applications. The results were quite promising. We used the E2-ENLG challenge as our primary testing ground, and the outcomes were encouraging. But we didn't stop there. We also applied our method to other datasets, such as WebNLG and DART, to ensure the robustness of our approach. This comprehensive testing allowed us to validate our method across different scenarios, further strengthening the credibility of our findings. Our research has yielded some significant technical results. Firstly, we found that our approach, which we call LoRA, can match or even exceed the fine-tuning baseline on all three datasets we tested. Interestingly, we observed that not all methods benefit from having more trainable parameters. In fact, performance can drop when using more than a certain number of special tokens for tuning. Secondly, we've discovered that our method of parameter-efficient adaptation, which uses a bottleneck structure to impose a low-rank constraint on weight updates, has a key functional difference from other methods. Our learned weights can be merged with the main weights during inference, avoiding any additional latency. Lastly, we found that low-rank structures are common in machine learning and can be beneficial in many deep learning tasks. This has led us to propose a low-rank adaptation update, which we believe is well motivated by the literature. In summary, our research has shown that LoRA is a competitive alternative to full fine-tuning, not only in natural language understanding tasks, but also in natural language generation models, such as GPT-2, medium, and large. In conclusion, this research introduces a novel, parameter-efficient approach for fine-tuning large language models. We've developed a low-rank representation to encode the parameter increment, which significantly enhances both compute and memory efficiency. This is a crucial step forward, especially considering the prohibitive costs associated with fine-tuning large models. Our proposed method, LoRA, has proven to be a competitive alternative to full fine-tuning. It has demonstrated effectiveness on both natural language understanding and natural language generation tasks. This is a significant achievement, as it not only retains high model quality, but also allows for quick task switching when deployed as a service. In essence, we've made strides towards making the fine-tuning of large language models more efficient and accessible. This opens up new possibilities for future research and applications in the field of language modeling. Thank you.